Thank you all for coming, and welcome to the SpecNet Fall Community Meeting. For those of you that aren't familiar with SpecNet, SpecNet's a voluntary organization, and we're interested in the use of proximal remote sensing to study ecosystem characteristics and processes. And we have these meetings to share information on the technology and science results that people are getting from proximal remote sensing approaches. And we're interested in, this is an exciting time for this field as technology is rapidly advancing, analysis techniques are advancing, and I think our ability to use these technologies and answer science questions is advancing, becoming rapidly more important. And so again, for me and the SpecNet board, welcome to the meeting. And I'll turn it over now to Loren Albert to introduce the speakers. Thank you.
Thanks, Fred. So for those who want to reference the agenda, it's in the original email. And first, I want to welcome Tommaso Julitta. He's going to tell us about towards an integrated network of flux systems. So Tommaso, you should have the ability to go ahead and share your screen when you're ready.
Yes. Hello to everyone. Can you see it?
Yes.
And
all right.
And before you dive in, I am also helping keep time to keep us on track. So I'll start waving frantically when you have like 1 minute left.
Perfect. Yeah, makes sense. Okay, so hello to everyone. I am Tommaso Julitta from JBF Spectral Devices. Big thanks to the SpecNet board to giving me this opportunity to be here presenting what JB is currently doing. And yeah, in particular, the idea of the presentation today is just to give you a bit of overview of the activities we are currently doing with the final focus of the realization of a flux network. And so try to really implement this. Okay, for the ones that are not familiar with JB, so JB is Hyperspectral Devices is a company founded in 2016, is based in Germany, and our main focus is the design and production of hyperspectral field instrument. We have 3 main products: the flux, the fluorescence box, which is devoted to the measurement of sun-induced chlorophyll fluorescence. Then we have the reflectance box, which is a simpler version of the flux without the high-performing spectrometer, which gives you a measurement of reflectance. And then the NOx, which is the most recent one, which is extending the capability of the ROX up to the near region, so up to approximately 1,750 nanometers. Talking about the flux, the specification. So as you can see, everything is inside a Peli case, customized. And basically here we have 2 spectrometer, one which is a QE, they're both from Ocean Optics or Ocean Insight. One is a QE Pro, which is really focusing on the emission of fluorescence. So the spectral range is just in between 650 and 800. You need a high spectral resolution and high signal to noise ratio to retrieve it. So this is really the one devoted to that. And aside of that, you have another spectrometer covering the full visible near range from 400 to 950 nanometer. It's a dual field of view system, so it's collecting solar irradiance with the cosine diffuser and with a fixed field of view of 25 degrees approximately the target. What you can get from it is the coming radiance, so the solar radiance, the reflected radiance, and then the reflectance. And then on these, you can compute as many vegetation indices or retrieval of fluorescence as you like, and you can get time series. This is an example of 7 years time series collected with the flux of John. Yeah, here I put some example of installation. You have here the cosine diffuser, which are looking up typically it's coming with a dust and burn protection system, so it's something that prevent the dust deposition on top of the cosign. We have some spikes that are trying to keep away the birds, which can be problematic in the field, whilst the downward fiber is just pointing to the target. Here, another example of an installation in an ICO site. So consider that most of the instruments are installed together with the eddy covariance system, because one of the main topics is really try to link the optical measurement with the flux measurements. Here, another example. In each figure, you can see that the sensor is a bit higher from the canopy. Here, another one. The previous one was in Kenya, in Africa, in Savannah. Here is the Savannah-like ecosystem in Spain. And this is one of the coolest pictures we have from Tambaramba site in Australia, where we have a pretty tall tower. Together with the instrument, we are providing software based on R, so completely open source to the user. But it's also coming with a graphical user interface to facilitate the processing. So with just few inputs, you can really process a long time series of data. But if you like, you can also dive into the code and try to understand all the steps. The steps are summarized here. So the instrument is collecting raw data, but then we are providing calibration coefficient to convert into physical units or radians. The ratio of reflected radiance and solar radiance is basically giving you the reflectance. Here you can see a diurnal course of reflectance. And based on this reflectance, you can calculate the vegetation indices, for example, NDVI, PRI, or all the others that you can be interested in. Then you can retrieve fluorescence with some already available retrieval method implemented. And together with this processing, also in the different steps are coming some quality flag criteria, which are used to filter out the time series afterwards in order to remove some outliers that might be due to unstable illumination condition during the measurement, saturation, or other situation that can provoke some imperfection in the data. So in terms of instrument, so we have about 70 flocks out now, and we are pretty proud of this graph where we in the last years we reached about 140 publication, which is really giving us the sense that we are going into the right direction, and the scientific community is appreciating our effort in this way. Here I put a slide that many of you probably already know, since this was a picture made during a workshop which was happening in 2023 in Colorado at Newark Ridge Station, and was a pretty cool workshop funded by Ameriflux FluxNet. And the goal was really try to link optical measurement and energy fluxes. I think one of the outcome that is probably coming soon is this paper that Zoe is leading, and maybe she will update a bit later. But in terms of the progress that we as JB made in the last year, I wanted to give you a bit of an overview. And these links brings me to some projects related to the European Space Agency. The European Space Agency is developing this FLEX satellite. FLEX stands for Fluorescence Explorer Mission. And the launch was postponed several times, but now should be fixed and is expected to happen in 2026, so in a couple of years. And the idea, the goal of this FLEX satellite will be to global mapping fluorescence, sun-induced chlorophyll fluorescence. And in particular, the idea is that we will be able to retrieve the full spectrum information of fluorescence and to derive different metrics based on that, like the peaks or the value at the oxygen bands, which are the values that are typically used in the research community. But also some other higher level products, for example, NPQ, electron transport rate, and several are still under development, so we'll see where we arrive before the launch. But this to say that ESA is also interested a lot in validation of this measurement, and this is why we were collaborating with them a lot. This is a sort of timeline of the project that we had with ESA. We started in 2017, so right after the startup of the company, providing to ESA some fluxes, which were used in different field campaigns in the last years for prove the concept of the FLEX in retrieving fluorescence, in deriving some higher level products. And this was really an effort, a community effort with a lot of other partners, research institute companies or laboratories. And after this workshop, basically we were working on this part of this project, which was really about the flux uncertainties analysis. So try to understand how accurate are the estimate of fluorescence made by the flux, and also some other aspect related to possible compensation on the atmospheric effect when the instrument is installed at higher distance from the canopy. This is something I want to show you, some updates. And then we really started this year another project, which is about the implementation of a flux network. So in terms of uncertainty analysis, basically here the point is try to understand how accurate or how far we are from the truth when we are measuring something. And there are different approaches to try to understand this point. One of that is to draft down a sort of tree diagram with all the possible source of errors that are concurring on the final outcome of the measurement. For example, if you are using a spectrometer, this could be the noise of the spectrometer, the nonlinearity of the spectrometer, the calibration in radiance, this kind of stuff, plus also the algorithms that are used to retrieve fluorescence, because all these steps can include or give some source of error. And what we try to understand is the sum of all of them, how they were propagating into the final result that we were getting. So what we did was to develop a flux simulator, which means a model that is mimicking all the characteristics of the instrument: noise, wavelength, accuracy, nonlinearity, cosine response, and all these things. Or we try to quantify most of them. And we combine this information with this simulation that we are getting with this emulator with some scope simulation. So basically, we know that we are overimposing a known fluorescence. We're trying to retrieve this according also to this, all these uncertainties. And as results, what we got was a pretty nice result, because we were able to retrieve in most of the cases, especially with some retrieval methods, for example, spectral fitting methods, the fluorescence with below the requirement of FLEX, which is already pretty strict, 0.2 milliwatt per square meter per nanometer per steradian. So this was a good result that we achieved in the last year. And the other point we were focusing on was really try to understand the impact of atmosphere when we are measuring fluorescence at higher distance. So here is an example of a measurement collected over 3 years in France on this tower, which is 100-meter tall tower, and the instrument, the flux, was really on top of that, measuring this oak forest. You can see the on the left, the PAR, so the seasonal trend during the 3 years, which is expected. And DVI is also showing a normal trend with tracking the phenology. But if you look at the fluorescence, in particular the far red fluorescence, you can see that it's turning negative during summer. And this is, of course, no sense because fluorescence is emission, so must be positive. Otherwise, it means that there is some problem in the measurement setup or the retrieval method. And actually, this is due to the fact that in between the canopy and the sensor, there is, in this case, 100 meters of atmosphere with oxygen. So the light which is reaching the cosine diffuser and the light which is reaching the fiber looking down basically is affected by different concentration of oxygen, which is then turning into negative fluorescence measurements. So what we tried to do was to test 3 different retrieval methods. Here is reported together with the publication. This was published in the last years. And the idea of these methods is really try to solve this problem. We try to apply them all. The PLS is a machine learning method, which is not affected by oxygen reabsorption because it's excluding this spectral region during the retrieval. BSF is using the curvature of the oxygen bands to determine the fluorescence and the absorption. And autotrans is something more a sort of radiative transfer model or atmospheric correction model, really working on the oxygen transmission. And what we found out as the output is that the 3 of them, they were working pretty good. The uncertainty was higher in some cases and lower in others, but the one that was working the best was the BSF method. This because is simpler to apply it on flux data because you do not need, for example, other information like atmospheric information, or you do not need to train the model a lot like for the machine learning. So this was also the other outcome. The last part, so the last project that we are starting, which is also taking inspiration from the lesson learned in the past, is really the implementation of a flux network. This is again a funded project by ESA. Ideally should last 2 years, in which we need to provide or to show the capability of building up this network. And in particular, we are really implementing a database with the capability of processing automatically the data which are coming. So the raw data that the flux is or streaming daily or the user is uploading. And this will also include in the processing the uncertainty propagation. So the results at the end will also come with the error budget and also the BSF. So this method for the atmospheric compensation. We are also working on a maintenance plan. So we are developing within this project a calibration device, a movable one. So instead of getting back the instrument, we should be able to have an instrument that is going to the site, and basically the people just need to insert the fiber, press some button, and then magically the calibration should be done. At least this is the idea. It's just started. We are working on that. And yeah, last but not least is the data policy definition, since this is something that we are working on. The idea is to have an open network. We have a lot of example out, both from the Fluxys community, but also other networks. And the idea is really to have a sort of open network where people can register, download the data in case cite the PI if is using the data. This is a consortium made by different company, laboratories, and research institute. And yeah, we're translating also everything from R to Python, which seems to be a bit more stable in terms of version. So coming soon, basically, we will have this questionnaire that maybe you will be also affected by that, because we will share this in the Flux community mostly, but also to other people that might be interested in. Really try to understand also the feedback from the user, how to share this data. we are developing this mobile movable calibration device. Here you see just a quick sketch that we have, but we will have an integrating sphere inside, lamps, also for wavelength calibration. And in terms of timeline, the project will last 2 years, but we are planning to have a first version, a beta version of this database running already in October 25, so less than 1 year, and we expect to have at least 10 sites to start with. Yeah, so this is the idea. And I think I finished, hopefully on time. And I thank you for your attention. And if you have questions, happy to reply.
Thank you, Tommaso. That was great. So we need to move on to the next speaker to keep the time, but there were a couple of questions for you, Tommaso, in the chat. If you look at those, you can go ahead and answer them there. And then we do have time for discussion after several of the talks. So we have 10 minutes for discussion at 13:25 Eastern time. So that's another opportunity to ask speakers questions. So I'd like to introduce our next speaker, Zoe Pierrat. Zoe, please go ahead and share your screen when you get a chance. And Zoe will be talking to us about proximal remote sensing.
Yes. Hello, everyone. Okay, I'm sorry for the technical difficulties. Zoom is no longer allowed on my work computer, so we're dealing with the browser. It's been a little bit of a journey. But thank you so much for having me. I'm excited to be chatting with you all, and SpecNet has been with me through my whole kind of academic career thus far, so it's very exciting to be coming and talking to you all again. I kind of like to think of this talk that I'm going to give as a little bit of the preaching to the choir, but I do still think that it's useful to kind of have this big zoom out overview of the way that I think of proximal remote sensing and put all of our work in context and how I've been thinking about the direction of the field recently and what we should be prioritizing as a community. So probably don't need to kind of explain all of this to you too much, but really to understand all of the changes that are happening in our climate, it's really important that we understand the biosphere in particular. And Dave Schimmel came out with this paper in New Phytologist that defines these kind of 4 main questions in global ecology. So what is the primary productivity of the globe and how is it controlled? How much carbon does the biosphere store and how can it change? How does direct human exploitation of the biosphere affect productivity and carbon storage? And what is the biological diversity of the world and how does it affect the function and stability of ecosystems? And I think this figure by Friedlingstein et al. Really kind of demonstrates this. It's from the global carbon budget. And you can see the uncertainties on all the different components of the carbon budget. And really the ones that kind of keep me up at night and, you know, I'm sure a lot of you think about is this uncertainty on the land carbon fluxes and the uncertainty in the land sink. And that really connects to, okay, we have to understand what's going on with all of the feedbacks on the land surface to understand what our carbon budget's going to look like and how things are going to change moving forward. So to tackle this kind of massive problem, I think remote sensing for plant sciences has been really growing exponentially over the past 20 years. These are some nice figures by Tao et al. That shows the kind of essentially just Web of Science search for results that say plant and then an array of different remote sensing terms. So different instrumentation terms, spectral terms, etc. And you can see this really expansion of remote sensing publications. And I'm sure that reflects all of your kind of experience in seeing how the field has developed over the past couple of years and the rapid advances in technologies, both at the satellite scale and the near surface scale. And so one of the things that I found really interesting in looking at these figures is there was really rapid growth in a few areas in particular. So One was multispectral instruments, which I think has just been kind of the main kind of foundation of our field since like the development of NDVI and kind of how all of that has proliferated. More recently, there's been a big growth in multi-sensors, so combining multiple types of remote sensing metrics, so like thermal with visible near-infrared, or solar-induced fluorescence with hyperspectral, etc. So really merging like multiple types of remote sensing, active and passive. Solar-induced fluorescence, that's been, I think, over the past 5 to 10 years, really blown up as we've been able to observe SIF from space with the development of all of these new and exciting near-surface instruments. And then specifically air and ground-based platforms. This kind of last figure shows the number of publications with different types of platforms. And you can see kind of the steady growth in spaceborne as we're launching new things into space, but there's been a huge, huge growth in ground and airborne platforms, which I think is very exciting for our field. And I think the explanation for this is that proximal remote sensing is very uniquely well suited to connect these key plant processes with what's observable from space to answer these big picture global ecology questions. So these are just the same questions from Schimmel et al. With a couple of key terms highlighted that I think are kind of really only effectively answered with proximal remote sensing instrumentation. So the primary productivity of the globe, we have these big spaceborne observations that are global now, but how is it controlled? I think we really can only understand these processes that happen at the leaf and canopy scale and over these super fast time periods where we have, rapid change and the implications for that on, all of these changes are happening super locally. And so kind of this fabulous figure kind of shows the spatial and temporal coverage that we can get with proximal remote sensing instrumentation. And so to get these regional global coverage, it's super critical that we have these satellite observations, but for these process-based understandings, there's really no substitute for proximal instrumentation. So more specifically, we kind of need to answer these questions. So what is the scale dependence of ecological processes and fluxes? So the spectral, spatial, and temporal, this is also super relevant as we're thinking about the next generations of spaceborne instruments for like, if we want to monitor plant carbon uptake, what information are we missing when we have these trade-offs between spatial and temporal revisits from satellite observations, and what actually is the resolution that's necessary to capture the key ecological processes that are controlling these fluxes? Or how can we supplement that with models that can kind of fill in the gaps for us? And again, what are the underlying physical and biological drivers under these remote sensing signals? And then I think proximal remote sensing is a really exciting test bed for developing new technology synergies and algorithms and models that's much lower cost than aircraft observations or launching a full satellite into orbit, where we can kind of see, okay, this is what we're trying to learn about ecosystems, and maybe we test those out with these tower-mounted systems, and that could lead to new mission development. So particularly combining proximal remote sensing with flux data unlocks a new suite of biological parameters that I think are super relevant for answering those kind of big picture global ecology questions. This figure, both figures actually were an outcome of the workshop that Tommaso mentioned, where we kind of identified, okay, these are like the 3 or the 5 sort of fields of remote sensing that can sort of unlock all of these different parameters for ecosystem science. And they're relevant kind of across scales, but I think if you zoom into all of these different things, so like plant stress detection, like that happens really at a super local scale, and the stress responses can be very rapid. And that's potentially not something that we're capturing with satellite or aircraft observations. So that's kind of really the niche that I think proximal remote sensing can fill. And I think this is particularly synergistic with existing co-located spaceborne observations and upcoming missions. So this figure sorry, my cats are like losing their minds in the back. So this figure from Natasha Stavros shows existing synergies on the International Space Station and a lot of the kind of proposed different metrics that we can determine from these spaceborne observations. But again, a lot of these different things like plant water use efficiency, which changes really rapidly over the course of the diurnal cycle, we're potentially not able to fully capture with spaceborne remote sensing alone. And so to understand what processes we're missing, I think that's where the proximal comes in. Proximal remote sensing is also highly relevant for policy and management decisions. So this was another outcome of this workshop that we hosted 2 summers ago, where we wrote a response to the National Strategy to Advance an Integrated U.S. Greenhouse Gas Measurement Monitoring and Information System. And we identified kind of 4 key areas where proximal remote sensing can contribute to this strategy. And a lot of our recommendations to kind of the initial draft plan were implemented in the ultimate national strategy. So that's super exciting. And I'm hoping will lead to kind of more funding opportunities to continue these types of work. Okay, I've talked a lot about all of the opportunities, which I assume, given this crowd, is probably not particularly new to a lot of you. But ultimately, I think it enables a deeper understanding of terrestrial ecosystem feedbacks on carbon, water, and energy cycles through space and time. But it is certainly not without challenges. And so kind of the current state is that we have a huge suite in different sensor types, viewing angles. There's a lack of standardization. People are processing their data completely differently. There's different calibration approaches. And I think a lot of this has come about because of this kind of rapid development in the field, where you have this trade-off between kind of innovation of what is the next cutting edge technology, which is not necessarily what is easily standardized and brought to the masses for more widespread use. And so I think it's improving, but generally we see these kind of disparate, disconnected, or largely inaccessible data sets from individual groups, although it is getting better, and we'll keep talking about that. But this is a serious challenge because in order for proximal remote sensing in general to be useful for global ecology in this global context, all of these differences in sensor types, calibration, and post-processing is making the data incompatible across sites. And so now for me being at JPL, if I wanted to use proximal remote sensing data for satellite validation or, testing anything, there's not really like easily accessible data kind of comparable to FluxNet or Ameriflux because of all of these different challenges. And I think this figure from Julia Mars really demonstrates that nicely, where we've got this huge range in different observations and inconsistency even among vegetation type. And oftentimes this data is also published in a publication, but it's not publicly accessible. And so to have kind of a broader database of, like, if I wanted someone who's fluorescence data from a bunch of different sites, it's a little bit of a wild goose chase to kind of figure out where all of this is and how to get access to it and everything. But I do feel like there is a strong path forward, which is very exciting. And I think that's really going to come from increased collaboration among Flux and remote sensing communities. I think the Flux community has done really an incredible job consolidating and having these grassroots organizing efforts with FluxNet and Ameriflux and ICOS and all of the things to kind of have these individual participation contributions to a more coordinated network. And then I do think that we need more federal support for proximal remote sensing. And it's very exciting to hear that ESA has been kind of investing in that, because I think it is great to have these individual participation, but all of these efforts have been successful because there has been some bigger coordinated grant. And a lot of this stuff has been kind of my pet peeve of the field and side time projects. And I think that ultimately it's a much bigger effort than like a couple of people's side experience. So some of the things that are working towards this in this increased collaboration among Flux and remote sensing communities. So it's the AmeriFlux Year of Remote Sensing, and there has been a whole bunch of different activities associated with that. There's a really great page on the AmeriFlux website now that has a whole bunch of different remote sensing products that you can access. And I think it gives a really nice summary for people who are potentially new to the remote sensing world. We had this workshop, as I've mentioned a couple of times, funded by the FluxNet Co-op and AmeriFlux and a couple of others on kind of linking all of these things together and kind of starting to get the ball rolling a little bit more on coming up with metadata standards and reporting and etc. And then there actually was kind of not a follow-up, but a little bit, another FluxNet Co-op funded workshop this past summer, the Great Thermal Bake-Off, which was much more narrowly focused onto like proximal thermal remote sensing, so thermal cameras, and doing rigorous like field experiments of a whole bunch of different thermal cameras and trying to develop very specific post-processing techniques to make thermal camera data more standardized across the board, which I'm really excited about, and to hear all of the outcomes from that. And then there's also Spec School. So I think that, yeah, having these education opportunities to kind of grow the field has also been super important. Another outcome of this workshop was this paper that's currently in review at New Phytologist, and the supporting information is what I would argue like my magnum opus of measurement protocols and best practices, and consolidates a lot of what I think the current state of the field is in terms of available instrumentation, how people should be setting up their instruments, what are the recommended post-processing techniques, and then consolidating where data is currently available. And yeah, I really just want it to be like a resource for people to have who are getting into the field and to kind of keep moving forward on these standardized measurement protocols, because I think that's super essential for the field to move forward. And then I also put an image here of an application that a friend of mine is developing, Jen Deal, one of the co-authors on this paper, that is a post-processing package for thermal imaging, which I think will also be super, super helpful. So I'm excited for that to come out. And then the last thing is publishing proximal remote sensing data in consolidated networks using these standardized metadata. And so there's a couple of things that are kind of in the works. So the global TLS database is a NASA-funded project that was in conjunction with the JEDI to develop post-processing techniques for LiDAR data and host this database. So if you're in the LiDAR world, I would definitely recommend checking that out. Another, I think, kind of gold standard is the PhenoCam network, which I think they've done a phenomenal job at getting different instruments linked up to the network, having standardized post-processing techniques, and making the data publicly available. One of the things that I worked on for this paper was just scouring the internet for where publicly available proximal SIF data was, and publicly available in that you can find it and download the data on your computer right away without emailing people. It's published under a CC by 4 license, and that is available. It's linked in the paper, but it's also just available on NASA's Jet Propulsion website, where you can click on the different sites and get the data. And if you have data that you would like included on this, I'm happy to update it, and we'll make a pitch for that as well. Okay, so main takeaways of my rambling is that I think proximal remote sensing is uniquely positioned to help us tackle these big questions in global ecology. but that data standardization and cross-compatibility is essential for all of this to work. And continued community engagement and participation in network science is the path forward. And I'm super happy to chat with any and all of you at any point in time, and I'm happy to take questions, and here's my contact information. Thanks, everyone.
Wonderful. Thank you, Zoe. For the sake of time, if you have questions for Zoe, please go ahead and write them in the chat or hold on to them for the discussion period that's coming up. Our next speaker is Petya Campbell. And Petya will be talking about proximal reflectance and solar-induced fluorescence metrics for assessment of photosynthetic function of high-latitude ecosystems, prototyping for ESA, FLEX, and NASA SBG.
Okay, great, thanks. And so it's my pleasure to talk about our research using proximal sensors and leaf level sensors as well for assessment of photosynthetic function. And so thank you for the opportunity. And so our team includes, on this project, includes researchers from University of Maryland, Baltimore County, NASA Goddard Space Flight Center, and University of Texas at Paso. And so we did study two types of tundra plots. And so the white polygons here, you can see one with the green circle in the middle, and dry polygons, you can see them further in distance. So then we also studied boreal forests. And so I'll talk about these three different sites and compare them. So we collected the data in 2022 and 2023. And so at leaf level, we used monitoring PAM, and the data includes steady state and maximum chlorophyll fluorescence, electron transport rate, yield to photosystem 2. We calculated non-photochemical quenching. And then we measured at canopy level using flux, and now everybody knows because Tommy explained about it. So we used a flux at three different installations. And so we had one installed in the wet sites here in the very left. You can see it in 2022. And Fred is like next to it. And here is the field of view of the instrument. Then we have another one on a very short portable tower here installed on the dry tundra site. And another one in 23 we installed at Caribou Creek in the Neon Bona sites, so Bona. And with the flux, we measured solar-induced fluorescence A and B, A par. We derived vegetation indices and used the reflectance with scope to derive canopy traits and also photosynthetic function. And to parameterize scope, we used our own field measurements and implemented it for tundra. And so without more introduction, here we will compare the results. And so we measured at the boreal, at the tundra during green up, which lasted until the beginning of August when the first snow fell. So here is the snowflake. And we had to leave and take the instruments and disassemble everything. After that, there were probably nicer days, but we missed the senescence and decline. When at the boreal forest, we measured both green up and senescence. So what you see is the absorbed photosynthetically active radiation as measured by the flux. And so there is no apparent trend at the tundra. You see the variation, maybe a little bit higher absorbed photosynthetically active radiation in the beginning of the season, when there is a steep incline during green up at the boreal forest, reaching maximum around mid-June, and then declining, and there was a sharp fall off when the snow started falling again, and the decline is with the decline in the deciduous vegetation, the senescence, and the loss of the deciduous species. And so further, we looked at NDVI, and so there is a gradual incline in the NDVI and with green up at both the wet and the dry tundra sites, with much higher NDVI at the site which was wetter. As compared to that, the trend at the boreal forest was very different. And so in the beginning, first we installed when there was snow on the ground, and so NDVI was very low, and the instrument was frequently not working because of the low temperatures. So this is something to consider, maybe heating up the instrument in such cases. Then there was a sharp increase in NDVI with after snow melt, and then gradually until it reached maximum in July and August, and then slightly declined with senescence, and this is the sharp decline in NDVI with the appearance of snow. So then we looked at the chlorophyll red edge index, and which did not change much throughout the season, slightly increasing for the dry side here in the lower figure in green, and increased more at the wet tundra sites with green up. At the boreal forest, it was much more pronounced, the change in the chlorophyll red edge index, and there was maximum reached around the end of July, and then decline started right away. So this was different from NDVI, when there is a much NDVI stays stable for a much longer time. So then, looking at the canopy chlorophyll derived with modeling through scope, we see the increase quite pronounced for the wet tundra site, and we see it also for the drier side, but to much lower levels. And also the root mean square errors of the predictions are much higher for the drier polygon, and it was much more difficult to obtain higher signals there. And so you can see also there is a higher error in the predictions earlier in the season, and decreasing with green up. Looking at the boreal forest site, you see the trends in the derived canopy chlorophyll. First, during snow melt, the model cannot give reliable estimates, and the root mean square errors are high. Then there is an increase in chlorophyll, reaching maximum around mid-July, and then decline, also quite steep, and reaching minimum by mid-September. And then again, when snow starts falling, the spectra does not allow for deriving traits. So then, looking further at the solar-induced fluorescence that we measured during green up from the tundra site, you can see that at the drier site, NG and G, there was much higher fluorescence magnitude measured, and also red fluorescence was much higher than far red fluorescence, which we found very interesting. And so at the wet site, the neon site at Barrow, maybe there was a slight increase in the far red fluorescence with green up, which was much more pronounced in the far red fluorescence at the drier side. And there was a decline in red fluorescence during green up, and at the drier side. And so we think that the difference in species composition and those two sides is causing, it's likely causing these differences. And also water may be a strong absorber of chlorophyll fluorescence, so something to follow up and research. Also, because of the very low chlorophyll levels at the tundra ecosystems, probably the reabsorption of chlorophyll fluorescence is lower, or there is lack of reabsorption, which causes the chlorophyll fluorescence A to be low. We see much
Right at time, Petya.
We see a different pattern at the boreal forest, starting with very high red fluorescence early in the spring and declining towards the end of the summer, and being very high again after the deciduous vegetation covering the ground senesces, and far red fluorescence increases with green up and declines with senescence. And so this is also very interesting, a new pattern to research. Looking at the relationship between the leaf level photosynthetic efficiencies, we notice the electron transport rate declines with green up, and non-photochemical quenching increases. And ETR was strongly related to solar-induced fluorescence B in cases when ETR is higher than 20. So these are the cases when there is no limitation due to lack of light or to low power levels. And so using the proximal measurements, we were able to derive estimates for as expected from the Flex Flores mission, and so we derived.
I'm terribly sorry, Petya. We are cutting into the time for the next person, so give you just a minute to wrap up while we switch. Go ahead and unmute yourself while we switch. Okay. Thanks so much, Petya. So I apologize, but we need to move on to next speaker. We have Cynthia Gerlein-Safdi talking about proximal imaging of SIF and spectral reflectance of coastal grasslands.
Hi, everybody. Can you see my screen? All right. So my name is Cynthia Gerlein-Safdi. This is actually my very first time attending SpecNet, so I'm very excited. Thank you very much for having me. I'm actually presenting in the place of my PhD student, Paul Seibert, who couldn't be here today. And I actually want to start with acknowledging kind of our co-authors on this work. Sophie Wu, who is here somewhere in the list of attendees. Hi, Sophie. Nicola Falco and Margaret Thorne at LBNL for a lot of the kind of in situ work that we've done here. And I thought I would start with a little bit of background about the place that we're looking at. It's a coastal grassland in California, and we're studying here the effect of global warming on soil, carbon, and nutrients. And the reason we selected this site is because grasslands cover about 40% of the planet, and they store about 1/3 of global soil organic carbon. And we have very little understanding of what is going to happen as the soil warm what is going to happen to this carbon, what is going to happen to the nutrients and the vegetation in those ecosystems. Our field site is at Point Reyes in California. So can you see my cursor, actually? Maybe not. Yes, okay, so this is San Francisco right here. This is UC Berkeley in the East Bay. And then this here is Point Reyes, and it's a field station from UC Berkeley. And we have this very nice meadow that we are looking at. And we've made a bunch of warming plots where we are warming the soils from the inside in those kind of 6-meter diameter circles. And we have groups of 3 treatment levels, so 0 degrees C, 3 degrees C, and 6 degrees C warming. And we have, gosh, I should know this, but I think 8 groups of 3. For this specific project looking at SIF, we've been focusing on 2 groups, one up here in what we call this upslope area, and one down here in this downslope. Now, the thing to understand is that there's actually a river here and an elevation gradient along this line here that I'm making with my cursor, meaning that the upslope is actually much drier than the downslope, and we're seeing quite a bit of differences in vegetation types that we have in these 2 parts. And then each of those circles here shows you the 3 different treatments, so control, 3 degrees C, and 6 degrees C. Now we have chosen, so a lot of our colleagues are looking at the biogeochemistry of the soils, and we are in charge of looking at the vegetation, and we've chosen to look at SIF because it's such a better indicator of plant stress over short timescales, especially in an environment where we expect to have a big shift in water content of the soils as well as nitrogen availability. More specifically, we're using a SIF imager by Headwall. And the great thing about this instrument is that it really allows us to look at a big area all at once, understand some spatial variability, and actually has a good enough resolution to even look at specific individual species at a given time and be able to kind of compare different species in one snapshot. Some specs of the instrument, we're covering wavelength between 670 and 780 nanometers with a sampling interval of a little over 0.05 nanometers. So we have 2,144 spectral bands. Here is an example of what the deployment looks like. So you can see here those kind of plastic tubing here, circles show you where those warming experiments are happening. And then this is the deployed instrument. We have this big tripod, a rotating base that allows us to take the picture, and then the imager on top. We have a field computer, and then we are going to scan in this direction. And the way the computer works, right, is that it's going to look at a single line of pixels and then going to rotate very slowly to make an image of the area that we're looking at, line of pixel by line of pixel, right? So it's scanning vertical lines and slowly making an image. So it takes maybe about 10 minutes to scan, maybe 20 degrees of image. And then we get our image over the area that we're looking at. So I'm not really going to focus so much on the results today and more focus on kind of some of the things that we've been thinking about, because it seemed like the right crowd to be kind of asking questions about some of the things we're doing. So quick overview again. So we have our sensor that's scanning this way, and then we are moving this sensor across the field of view. And then, of course, we have our spectral position as well. So for each pixel, we have the whole spectrum. Here's a quick overview of our retrieval pipeline with the hypercube that we're generating, the dark reference and our calibration that go into a radiance conversion. From this hypercube, we use the white panel retrieval and the kind of delineation of our area of interest to get our SIF retrieval. And then we're incorporating some viewing angle, geometry, canopy parameters, and escape fraction to kind of get from the observed to the total SIF. because what we're interested in the end is how productive is the ecosystem, and is there a change in productivity across the 3 treatments that we have for the soils. Here is a quick video that Paul made that shows you a little bit what the instrument looks like. And unfortunately, we don't have this kind of real-time pictures when we do this. So here you have the spectral range in this direction. And then this here is showing you the kind of vertical, right? The vertical spatial direction. And then as we're moving, right, we are, this is all changing because we're looking at different pixels. So different horizontal pixels. And then you're showing at the bottom kind of how the figure kind of comes together. And so we have the false color, NDVI, NRV, and SIF at the end. And then the red line here is capturing a single pixel and then showing you the spectrum for that place. Oh, we're going over the white panel. Here, our white panel reference. So you see it showing up. And then we're going to move, okay. We're going to move, oh wait, all right. So I'm gonna keep on going if I can. There you go. All right, so we have those images similar to what we're showing, and we can look at a few different indices thanks to the spectral range that we have. In terms of results, again, I don't really want to focus on this, but we found that where it's wet, SIF seems to be mostly correlated with PAR as opposed to the upslope, which is dry, where SIF really seems to be responding to VPD instead. But I wanted to kind of mention some of the things we've been thinking about a lot, because I think this is the right crowd, and we're hoping to kind of get some discussion started, maybe continuing them at AGU. The first one has been sun viewing geometry. It's something we've been thinking a lot about because we have this kind of 3 plots that we're looking at from kind of very different angles over a day, right? Because we place the tripod and then we scan through our 3 plots at once. One way to maybe address this is to use relative SIF instead. But it's still something that we're trying to grapple with. We're also curious to see, you know, what the angle of the white panel itself might do on the retrievals. So something that that's been on our mind and that we would love to get thoughts about. We've also been looking a little bit at different ways to get at, again, total SIF as opposed to the observed SIF. And we've been using the F-escape approximation of NRV over FPAR as a way to get to total SIF. And again, this is something that we're still kind of exploring and would love feedback on. And then, whoops, just some final thoughts. You know, we have quite a few things we're still thinking about with this data: practical, geometric, and atmospheric correction, influence of panel geometry and position, averaging over spatial scales. We have all those different sensors. Should they be treated differently, right? All 1,600 spatial sensors, and we're losing information. Should we average? Should we not? Thank you so much.
Thanks so much. Thanks so much, Cynthia. Next, we have Sergio Vargas Zesati telling us about Arctic spectral astral web mapping application. Sergio, please go ahead and share your screen. And just a reminder to everyone, we do have a discussion at 13:25 Eastern Standard Time for follow-up questions or final thoughts from presenters, etc.
Thank you, Loren. Can everybody hear me? All right. And is my screen there? Yeah. Okay. Thank you for the opportunity to speak today. My name is Sergio Vargas. I'm a research assistant professor at the University of Texas at El Paso. And I'm excited to talk to you today about a really neat tool that our team has been working called the Arctic Spectral Library web mapping application. I want to thank all the members of the team that have made this possible, and also collaborators like Carl Huemmrich that is present here. Today I'll begin by just giving a brief background. I think the speakers so far have done an excellent job of summarizing sort of the main challenges related to proximal remote sensing. So I won't go into too much detail about that, but then I'll kind of identify some of the challenges related to hyperspectral reflectance. I'll introduce our app through a quick video demo. I'll summarize some of the features that are shown in the demo, and then I'll end with some of the future directions that we're planning on. So, as you've heard already, research shows that some, remote sensing has been used a lot across different ecosystems, but in the Arctic, research shows that it's experiencing dynamic and environmental ecologically significant changes due to climate change. Due to that, a lot of one of the main overarching research goals is to better understand how these ecosystems are responding and how vulnerable and resilient they are to change. So remote sensing has been a very popular method among Arctic researchers, and particularly hyperspectral reflectance. This figure on the right kind of gives you an idea of the various types of scales, spatial and temporal scales that hyperspectral reflectance can be collected on from automated systems like trams, or collected from towers, recently from UAVs, and then also scaling up all the way to the satellite. So you can imagine advances in remote sensing allow for a lot of data collection, but managing and visualizing large amounts of hyperspectral data originating from various sensors and data collection methods remains a big challenge. Additionally, there are limited tools available for data discovery and overlap between data sources. So the research community has recognized a demand for improved tools for hyperspectral data discovery, access, and archiving to facilitate rapid search, filter, and extraction across different locations. This demand is further catalyzed outside the Arctic with the increase of hyperspectral imaging satellites being planned, advances in UAV and aircraft-mounted sensors, and then also advances in hyperspectral imaging analysis using deep learning. So motivated by some of these challenges, we developed Astral, essentially a web mapping application that integrates in situ spectral reflectance data with corresponding metadata for every single record in the database. We currently host close to 10,000 in situ spectral reflectance data records collected mostly in Alaska, spanning multiple decades. Some of the objectives of this project are to support Arctic terrestrial ecological research by leveraging existing spectral data sets, facilitate data discovery by creating eco-infomechanic tools that co-locate in situ data with airborne data such as AVIRIS hyperspectral. Their goal is to enhance data and metadata visualizations. So streamlining data quality checking and summarizing metadata for all records. And the fourth goal is to facilitate data sharing. A cool feature of our app is that it's based on a structural framework that was developed by Ecosys to enhance data fusion, metadata standardization, and app interoperability. So now I'll play this short video.
Sergio, sorry to interrupt. I just wanted to see if there's sound associated with the video because we're not hearing that part if there is.
Yes, there should be. I guess I could just talk through it. So here we're showing basically there are three main parts to the app. You have an interactive map shown here. You have a table summarizing the different data records in the app, and then you have some filtering features and legends showing layers. You can interactively turn off layers on and off. You can filter the data using these fields here. This feature also helps with discovering data and overlap between in situ and average flight lines, for example. You can click on the flight lines and get metadata for the particular flight lines. You also have the ability to download the average flight line link directly from the app. You can filter by location or other fields like initiative, discipline, or NSF award number. We can filter by year. Here we're showing data for Aqua. You can click on the points and you'll get pop-ups showing metadata for those particular records. And also interactive maps and images showing examples of what the reflectance represents.
Thanks, Sergio. You've got about a minute left.
Right. I apologize about that. I wasn't aware the audio wasn't working. But here, I guess I'll just give a quick summary of the app. Astro relies on a system architecture that follows protocols that were created for other web mapping applications, such as AOV, BAID, and RMAP. It incorporates a structural framework and standardized methods developed by Ecosys. We host close to 10,000 in situ spectral reflectance data across Alaska. The app displays locations and metadata for average flight lines across the Arctic. It also provides data quality checking tools, and it is highly adaptable. It can be customized to meet needs of different research communities. And future directions are to expand the capabilities, develop the capacity for users to sign in and out, improve summary statistics and reporting options through dashboards, provide a more pleasing user-friendly experience, and reinforce the link between Ecosys, SpecNet, and Astro.
Thanks so much, Sergio. So our final speaker before the discussion is Jose Eklund. Please go ahead and share your screen. Jose will be talking to us about site spectral infrastructure and spectral data collections.
Yes, can you see my screen? Perfect. Good, I think. Well, thank you very much for the opportunity to talk about sites. Sites, it's the Swedish infrastructure for ecosystem science. Is it a national network of research stations across Sweden? And it was established in 2013 to support field-based ecosystem research. It consists of about 10 research stations, and it provides open access to data and metadata, field resources, and data harmonization and standardization among the stations. Long-term monitoring and experimental studies across diverse habitats and climate zones in Sweden. Those are including agricultural lands, forests, wetlands, mountains, and lakes. And specifically, Site Spectral, the thematic program, focused on addressing the challenges related to environmental monitoring at various spatial and temporal scales, and by managing a multi-platform of proximal remote sensing infrastructure and data processing toolkit. So basically, this approach provides valuable data sets that bridge the gap between the plot level measurements and satellite scale observations, which of course are crucial for understanding our ecosystem dynamics and at different scales. So for that, we use the phenocams. Here on the screen, I kind of show the different stations that belong to the Site Spectral in orange. And some of the icons just reflect which type of measurement platform is being used on those stations. So we have phenocams, we have fixed multi-spectral sensors, we're using UAVs, and we are starting to produce as well satellite data products. So basically, for integrating all these technologies, Site Spectral, enabling comprehensive environmental monitoring and facilitating the upscaling of data. And I would show you some examples of the measurements and of a little bit of the infrastructure as well. So, for example, here we can see the calibrated reflectance of in the visual spectrum in separated wavelengths. So we have such measurements. This typical NDVI. One thing that we have been working with the sensors from Sky and Decagon in our infrastructure, but as you know, they are no longer being produced, and so we kind of reach out as well to you if you know of a kind of replacements for those. We will be much happy to hear about that. This is just an example of one of the towers where we have our sensors, fixed sensors in place. This is a study for the birch forest overstory and understory phenology. It's a bit old study, but not less relevant for what we are discussing here, which basically in this green area, we can see the onset of the greenness on the vegetation. We're talking about a forest in the northern Sweden. And this kind of has the different gradients of the greenness. But as well, we can see here in red, there is the GPP, the gross primary production, and as well how it goes with the temperature, and then we have the day of years. But what is important here is like how the overstory and the understory drive combined with the NDVI and the ecosystem to drive the gross primary production profiles. So basically here we have we can see that early in the year, well, basically it's quite cold, it's a lot of snow, but as soon as the snow recedes, then we see the kind of a spike of the understory. and NDVI, and then it comes continue until it just mixes with the overstory. So basically, if you can see the F bar as well, we can see for the understory. So it kind of it goes really nice until, of course, it's blocked the sun, and then it reduces the photosynthetic radiation. But for the overstory, it goes the opposite. So thank you for this. Thanks for this type of measurements that we have as well understory and above the canopy. We can basically understand a little bit more, kind of put a little bit more of effort on this part of the gross production, the gross primary productivity that basically it's drive both for the understory and the overstory. Other practically use of that we have been using here in universities is how these proximal sensors can be used for helping us to have the fill up like the gaps in the time series of satellite images. Here we have a satellite images in black and green, which is MODIs, and then on the points in red is the ground sensors and that we are using. So we can see how it kind of it really followed nicely the vegetation signal of the satellite observation. So basically we can improve our models and as well improve the validation and start to fill in some gaps that probably we have clouds or missing data from the satellite can be just basically fill up with the ground measurements. So it's very useful for improving the time series of something that we do at least once per year, 2 times if we are super lucky with the weather conditions in all of our stations. It's the sensor calibration of the instruments. So basically, uncalibrated sensors is really difficult to have a consistent time series. So basically, we perform simultaneous measurements of the 2 or more sensors. So we have the a reflectance plate, and you might have as well kind of do all this for calibrating your sensors. So we have a yearly coefficient for calibrating our instruments. So it's we have seen that actually these calibrations are more accurate than manufacturer calibration, and that can be done easily in the field. So this is kind of an example of some of the setup that can be done. Here is another example. Yes,
almost out of time.
I'm coming. Yes, just quickly, just this is an example of the green chromatic index for an insect outbreak. So we can see here that how it was in 2015 really well following the normal phenology, but here in 2012 when there was an insect outbreak, just basically the insects eat the leaves, and basically well, there was no more greenness, but and then the red chromatic index, something that we derived with this information, is as well kind of down here. I can skip this one. You know that there is a lot of different products from using drones. Some of the satellite products that we have been trying to do using phenological parameters from Sentinel, using TimeSat and the plant phenology index. and the Copernicus land monitoring system is like this. It's the start of the season, the productivity, and the end of the season, and the amplitude. So you can find those as well. And we have different data labels that we produce, and we put it into the data portal. And as I mentioned, and Zoe, please add us in your database, because we do have a data portal with all these open source, so you don't have to ask anyone, and we are continuously uploading all these multi-platform data. Well, yeah, that's it. Thank you very much for your attention.
Thank you so much, Jose. So now we have the opportunity for more questions, discussion, follow-up questions. I know I had to very rudely interrupt some of you. Apologies about that. But we have, I suggest about 7 minutes of discussion now, followed by about a 7-minute bio break. We will start at 13:45 for our next talk with Chris Wong. So if you have a question, please raise your hand or feel free to write it in the chat. I think it works well to have both going at the same time. You can use the Zoom feature to raise your hand as well if you want to ask your question verbally. And actually, Jose, it looks like you have a few questions for you in the chat as well. Oops, you're muted.
Yes, I'm trying to respond. Yes, the insects removed some of the leaves, and so and as well kind of dried the trees, so it's start kind of to become less green, and that's why we have a kind of a reddish color. Not only that it changes with the fall, but it's as well like it's basically not having a water. Basically, it's and as well they eat some of the leaves.
Well, part of my question here was I'm not real familiar with the red chromatic index, and but does it actually track the leaves turning red in the fall? Is that what's happening? Okay.
I have a question, actually from one of the earlier talks. Tommaso, there were some great questions for you in the chat, and I encourage folks to read those if they haven't seen those. There's some nice discussion there. But I was also interested in hearing a little bit more about the in situ calibration you're working on. I missed, was that mostly targeted towards radiometric calibrations, or was it for other calibrations as well for the flux?
Yeah, thanks for the question. So it's mainly for radiometric wavelength and nonlinearity check, calibration and characterization. So typically this is done with the instrument that are shipped back to us for a periodic calibration, like every year, or depends on the site. But yeah, if we have something that we can bring, we avoid the problem of interrupting the time series, of travel cost, and this kind of stuff, custom, so on. So the idea is really to make something that is movable. Yeah, and mostly, yeah, radiometric calibration is the one which is more affected if the instrument is left in the field for a while. Yeah.
Thank you. And I'm curious, do you envision that people would do that more frequently than, like, would they be able to have one that they could potentially loan from you to just do a quick in situ check, or would they purchase one and do their own like weekly or monthly checks, or just flexible?
Yeah, well, consider that what we are planning to make, at least at the beginning, is something that itself will be pretty expensive because there will be 2 spectrometers inside tracking the sphere. The integrating sphere itself is not too cheap. The wavelength calibration lamp. So ideally, I think that this we develop first, then we can probably try to find an agreement with the people participating to this network, like discount for offering this service. We are discussing with ESA if can eventually also support and fund part of this, and maybe we will make more than 1 unit in the future just to have the capability of calibrate more instruments at the same time. But for the moment, yeah, we just started, so this is more or less the idea. We do not have yet the final plan.
Thank you. Yeah, maybe 1 per continent or something, but that's exciting.
Yeah, something like that, yeah.
Yeah, it's a great idea.
Maybe just one comment, which is not referring to any talk, just to promote a symposium, a workshop that there will be, maybe most of you already knows, in Vienna in June, is organized by European Space Agency Living Planet Symposium. The good thing is that it's super cheap, so it's affordable, even if it's of course overseas for you. But yeah, think about that. Deadline of abstract is coming soon in December, but I think it's a nice workshop to attend as well, in this field especially.
Thanks, Tommaso. If you have a link for it, I encourage you to drop it in the chat. And for some of the other speakers too, if you're showing videos or things that you wanted to promote, feel free to drop those links in the chat. Like Sergio, if you wanted people to be able to go look at the video with the sound, for example, feel free to drop that link in the chat. I'm going to take the opportunity for another question. Petya, in your talk, you were showing some far red differences, if I caught that correctly. And I was curious if you could tell us a little bit more about that and what you were thinking the explanations were.
Well, the 2 signals in the red and the far red fluorescence are different magnitude, and so I was just showing that usually people report the far red, the A fluorescence being higher. Well, we measured the B fluorescence being higher, and one of the potential explanation is the very low chlorophyll levels, but I have spoken with Tommy about it, so he suggested that, and other people have seen it also in high altitude vegetation, like grasslands and others. What was interesting to find for us was that there was strong relationship to ETR of SAFB, and so we'll follow up to see if this is the case in other ecosystems too.
Thanks, folks. This is a good time for a 5-minute bio break. Feel free to discuss in the chat if you want. And we'll start right back at 13:45 Eastern with Chris Wong. As people trickle back, I'd like to introduce Chris Wong. Today, Chris will be telling us about Midnights, a low-cost nighttime LED-induced chlorophyll fluorescence (LEDIF) system for monitoring phenology and drought stress.
Thank you. Should I just go ahead and get started then? Okay. Yeah, thanks for inviting me and giving me the opportunity to present. This was work done during my time at UC Davis in California. I'm now at UNB. And Midnights is a system we kind of developed, led by two of our master students. They're now finished and are working elsewhere. So Devin McHugh and Logan Brissett, they're kind of like the leads on this type of work that I'll be presenting today. And today I'll be talking about some of the motivation, theory, and then the methods of Midnight system, and then some of the applications that we've used it for. So I don't have to go into a lot of detail, but a lot of the motivation of this type of work and in SpecNet in general, I think it's safe to assume, is trying to estimate photosynthesis and photosynthetic activity. And a lot of it is tied to the fate of light. So when light hits a canopy, some of it's absorbed, which is then used for photosynthesis, some is transmitted, some of it's reflected. With optical remote sensing, we can look at the reflectance of light and assess kind of the pigment dynamics to try and use those as proxies of photosynthetic activity. And then we can use solar-induced fluorescence to look at this chlorophyll fluorescence signal to help infer information about photosynthetic activity. And then in the past, we can also use active fluorescence systems, so PAM chlorophyll fluorescence, which is an active light source that we can modulate light intensity and saturation pulses to get at a couple additional pathways like heat dissipation, chlorophyll fluorescence, to also try and get towards this photosynthesis pathway. So that kind of led to the motivation of the Midnight system, because it's a system that can measure chlorophyll fluorescence from a distance, but it can also work at night. And this has a couple different benefits that we see. So it's a light emitting diode, LED, induced chlorophyll fluorescence. And by operating it at night, we kind of get into that PAM fluorescence world of measuring kind of this F0 parameter, which can represent baseline fluorescence signal of a plant or a leaf in a resting state. And that can help get information about kind of just how the plant's health is looking like. With a signal like SIF, for example, it's going to be taken during the day. So it's really impacted by light intensity from the sun. So with the nighttime system, we might be able to get at more towards the baseline type measurements. Depending on the type of sensor you set up, we can monitor the spectral signature of chlorophyll fluorescence. So this is a paper that kind of shows what a chlorophyll fluorescence signal looks like. We have a kind of this double peak, one in the red and then one in the far red. And those can be used to calculate just overall chlorophyll fluorescence emissions. We can also use it to look at red-far red ratio, and these can be linked to plant photophysiological state, which is then connected to photosynthesis. And because it's a nighttime system, I kind of mentioned it can monitor that inherent state of the plant. So it could be looking at kind of the long-term stress, like whether it's something that's impacting the plant in terms of just its overall health and not impacted by those like diurnally changing conditions. The Midnight's work was motivated by two papers that came out. The first was from John Atherton over in Helsinki with Albert Porcar-Castell. They called it the late night disco system. It had a few media articles on that, but it was like a conceptual methods paper just introducing the theory and applications of using kind of these high intensity light sources. So they on a tower set up these strong lights that can shine light on entire trees in different colors, so blue, green, red. This is just showing the light intensities from the light sources across the different colors, and then showing some chlorophyll fluorescence emissions. So really kind of showing that we can measure chlorophyll fluorescence at night using some type of active light source. Another paper that came out a couple years later by Romero et al., they kind of took a similar system, focused only on the blue light, and mounted their LED-IF system on a tractor, looking at irrigation treatments in a soybean crop. and showed that they were able to detect different chlorophyll fluorescence emissions based on just the irrigation treatments in crops. And these kind of papers kind of motivated us, in addition to a new sensor that came out. So Apogee, we're not sponsored in any way, but they released a new sensor, a photodiode sensor that was designed to measure red, far red signals. And we thought this could potentially be used to measure chlorophyll fluorescence emissions. And this is kind of showing the responsivity of these sensors. So it covers the red and then the far red. And based on the chlorophyll fluorescence emissions spectrum, we see that the far red overlaps really well in terms of the second peak. But unfortunately, the red falls just outside or just captures the corner here. So for the rest of the talk, I'm not really going to talk too much about LEDIF red from the photodiode, just because we couldn't really get it to work that well just because of this, this offset in the signal. So most of the LEDIF from the photodiode will be focused on the far red. And as I mentioned, this work was led by two master students who have kind of led 2 experiments that I will go over and have published this work, which I'll refer to in a bit. And taking a kind of a side track, Midnight's, the name, was motivated by 2 reasons. It works at night, and we eventually mounted it on one of our other instruments called T-Swift. This is kind of similar to the Phlox type systems and kind of photospec, where we're able to advance it a little bit more. We put it on a RGB camera that can swivel, so we can target individual plants and plots and trees, zoom in really high resolution, and take scanning information. We collect RGB imagery. We can get hyperspectral reflectance, as well as retrieving SIF with this instrument, and it can scan hundreds of plants per day. So we eventually moved Midnights onto the T-Swift system, so there's a bit of a link there in terms of naming motivation. So going back into the Midnight system, this is kind of the bulk of the system. We designed it to be fairly low cost. The photodiode sensors, they cost a few $100s, I believe. And what the Midnight system consists of are blue LED lights pictured here. This is an early picture where we, in the future, added more lights just to increase the intensity of the light source to improve the signal to noise ratio. And then located in the middle are 2 photodiode sensors. One is the far red light photodiode, and then the other is a PAR sensor. Eventually, we added on a fiber optic cable that measured hyperspectral data connected to a Ocean Optics flame spectrometer. Here's a picture of the Midnight system in the field, where we have the sensors and light sources mounted above canopy, and then a little housing box that holds the spectrometer and a Raspberry Pi that operates and controls the system and logs all the data. And then here is a picture of the system at night in action. So we're shining blue light onto the canopy, which then our sensors can measure fluorescence emissions. What's really cool with this is focusing on kind of a hyperspectral just to show what type of information we get. At nighttime, we turn on the blue lights and we get this really big spike here. And this is basically the blue light being reflected off the canopy. So with the hyperspectral, we're able to see just blue light emissions or reflectance. And we're kind of using this as a way to indicate canopies, to represent canopy structural change, just in case the canopy structure changes a bit. And then when we zoom in really closely to the red, far red region, we get this tiny little chlorophyll emission signal. And what's really cool is that this is pure chlorophyll fluorescence, not impacted by anything else, because we're shining blue light, and in theory, nothing else should really reflect. So anything that we're seeing outside of this blue light region is going to be that chlorophyll fluorescence emissions. So that's how we can kind of infer and monitor chlorophyll fluorescence. With the photodiodes, this is kind of showing the PAR response, and then the red, far red responses as well. And as you can see, the red signal unfortunately just falls outside of the fluorescence emission signal. So with the midnight system, we activate it at midnight. It could be done really anytime at night, but we just selected midnight because it's the start of a new day. So it made just data processing a bit easier. And what we can see is with the different types of parameters from the hyperspectral instrument, when we turn on the light represented by this gray region, we see an increase in reflected PAR. That's just blue light being reflected back. We see in the far red this increase in emission signal, as well as in the red from that hyperspectral instrument. The photodiode sensors, they also show a response when the light is turned on, which is really nice to see. We did notice that, at least with the hyperspectral instrument, we did get this tiny bit of a drift over time. So we did correct for that by just applying like a linear fit to act as a baseline to try and tease out any type of drift. Using times before and after the light source was turned on. So this experiment, so we had two experiments that we used midnight. The first one I'll talk about was led by Loren Brissett, a former master's student. This was done in her backyard. We did this experiment during, I think, 2020 or 2021. So we had trouble trying to do field experiments. So Loren graciously volunteered her backyard to set up this kind of experiment to test out midnights. This is more of a proof of concept paper, just seeing if midnights could work. So in Logan's backyard, we got a plant, built this structure above it to house the midnight system. So with midnights, we were looking at the far red signal. We set up a MoniPam system, which is a PAM fluorescence system that can measure fluorescence continuously 24/7. Logan collected handheld spectrometer data at nighttime, at midnight and midday, as well as Li600 data for chlorophyll fluorescence and stomatoconductance. At nighttime, we cover the plant up with this black tarp just to make sure we're not getting any external light sources from the house or from street lights, just to make sure it was a completely dark environment when the LEDs were turned on. And we did this over a terminal drought stress. So this is what the experiment kind of came up with. We broke it down into 3 periods: a pre-drought period, which served as a baseline, the drought period where we stopped watering the plants, and then a post-drought period where we tried to rewater and recover the plants. Unfortunately, the post-drought didn't work too well. I think we just pushed the plant a bit too hard. So we get a bit of mixed signal. So I'm not going to focus too much on the post-drought. But anyways, with the photodiode-based LED-IF, we get this really nice drop-off in terms of the chlorophyll fluorescence emission signal during the drought period. The hyperspectral instrument also detects this same decline. F0, which is measured from the MoniPam, shows a bit of a decline as well. And then FV over FM, another chlorophyll fluorescence parameter, also shows decline. And then getting into some other parameters, photochemical quenching shows a decline. NPQ, protection pathway that dissipates excess energy, it increases. Stomatoconductance was a bit more noisier, but also showed a decline. NDVI, basically no response, meaning that any change wasn't really visible or impacting greenness of the plant. We calculated the photochemical reflectance index as well, PRI, which also shows a response. So overall, this proof of concept of the midnight system does show that it was able to track kind of drought responses in at least this backyard experiment. Kind of linking it, I'm not going to go over every single panel here, but we essentially looked at a bunch of correlations with LED-IF from the photodiode on the x-axis to all the previously mentioned parameters on the y-axis. And we found that the most strongly significant relationships were with the LED-IF hyperspectral, kind of indicating that this photodiode system could be a cheap, low-cost alternative to a hyperspectral sensor, at least with the far red. It links to photochemical quenching, FE over FM, and PRI, which are all indicators of kind of the photosynthetic activity, capacity, and pigment dynamics. So yeah, that's kind of the first experiment. The next experiment that we did, we basically moved midnights out into the field. This was work led by Devin. We published the paper in JDR Biogeosciences led by him and I. We basically put midnights in the field, equipped with the photodiode, with the hyperspectral, which we have since automated, mounted it at the base of T-Swift, that tower-based system. And at the same time, we had eddy covariance as well, providing GPP and some meteorological data. So that's a picture of the setup, Devon there, and then just the system in action. And with the chlorophyll fluorescence emissions signal, because we were able to measure continuously at nighttime, we see that over the course of the experiment from August to October, we see that the radiance in the PAR region declines. We see chlorophyll fluorescence declines. This is showing kind of the difference of the chlorophyll fluorescence emissions based on a baseline day that we just selected as August. And just to make it a bit more visually appealing, we calculated the red far red ratio and show that it increases over time during senescence. So because we're seeing a decline in this visible region here, that's likely due to canopy structural change, whether it's due to the plants growing or wilting or senescence itself. We didn't really tease it out, but we do see some type of structural impact. So what we ended up doing is using the red and far red signals and dividing them by PAR from this to try and to account for any structural change and to kind of normalize it or standardize it to a purely physiological signal. So just kind of showing how the experiment looked over the course of time from, I guess we went from July to October. Everything kind of declines, especially soil moisture, GPP declines. The T-Swift system shows a decline in SIF as well as NDVI driven by the phenological change. And then midnights, for the most part, the hyperspectral represented by the purple colors, the far red to PAR shows a decline. The red signal also declines. The red far red increases. The photodiode system, unfortunately, didn't really show much of a response. I think we were the sensor system might have been a bit too far from the canopy potentially. So there's some improvements needed to just adjust kind of maybe the integration time, the light intensity of the photodiode system. So there are room for improvements for that in particularly. And then kind of going through just different relationships of the different LED IF parameters to SIF. I'm not going to go in detail for each of these, but this top left one shows LED PAR to SIF relationship. And that shows an actual pretty strong relationship suggesting that there is a structural impact on SIF. The LED IF red to SIF shows an even stronger relationship. So this LED IF signal integrates both the structure and physiological variations. Here we have the red to the PAR correction, and that's trying to tease out the physiology. So that results in a slight decline in the relationship with SIF. The same thing with the far red signal, very strong with just far red. When normalized to PAR, it decreases a tiny bit. And then the red far red relationship as well. So the overall summary from these two experiments, Midnight's LED IF offers a way to evaluate baseline chlorophyll fluorescence. And with a hyperspectral instrument, we can look at magnitude and spectral pattern and get towards kind of the fluorescence emission spectrum. The photodiode, the far red seems to work, the red not so much. And there's a lot of room for improvement, but it's a hard balance to between light intensity versus inducing light acclimation. So it's a tough balance that we have to consider. And ultimately, I think there are some potential applications for a midnight type system for modeling chlorophyll fluorescence spectra. It provides a low-cost monitoring system for evaluating vegetation health, and it could potentially complement SIF sensors. And just in the last week, I saw this paper come out from that Helsinki group again, where they leverage their kind of nighttime system and use it to kind of work with the fluorescence spectrum modeling. So thanks for listening. My contact's up here. Just want to acknowledge that many collaborators from UC Davis and USDA, and then funding sources from NSF and USDA as well. Thank you.
Thanks, Chris. You have a couple of questions in the chat too. Feel free to answer them there. And after this set of talks, we will have a little bit more time for discussion before we wrap up. So if people have other questions, we can ask them then as well. Our next speaker is Koong Yi, telling us about integrating tower flux and proximate remote sensing to address key ecological questions.
Okay, do you see my screen and hear me? Okay, great. Thanks, Loren. And hi, everyone. My name is Koong Yi, and I'm a postdoc with the Huemmrich Flux Management Project at Berkeley Lab. Thanks for organizing this great meeting, and I'm excited to share my research on linking flux data with proximal remote sensing and some resources from the Huemmrich Flux Management Project that can support research in this field. So let me start by briefly introducing the eddy coherence technique. So if you imagine airflow in ecosystems, airflow can be viewed as a horizontal flow of numerous rotating eddies, with each eddy having three-dimensional components, including a vertical wind component. If you take a close look at an individual eddy, we can determine the vertical flux if we know the amount of gas of interest in the air parcel and how fast they move. In this manner, flux towers can measure gas exchange between the land surface and the atmosphere, including CO2, methane, water, and energy. These fluxes are recorded at high frequency within a flux tower footprint, typically spanning an area of up to a few kilometers. To better understand ecological processes under global change, the ultimate goal of the flux research community is to produce flux information everywhere, all the time. Flux measurements provide high temporal resolution, but they are confined to small spatial scales. In contrast, satellite-based remote sensing offers broader spatial coverage, but at the cost of lower temporal resolution. To achieve this vision of everywhere, all the time observations, it's essential to integrate measurements across various spatial and temporal scales. However, it is challenging due to differences in their measurement principles and assumptions, scale discrepancies, and so on. So recent advancement in proximal remote sensing may help address these challenges by delivering high-resolution near-ground data. In addition, proximal remote sensing offers several distinct advantages that enhance its utility in ecological studies. For instance, proximal remote sensing is non-invasive and cost-effective, making it ideal for long-term monitoring of ecosystem processes. They are also highly adaptable to a wide range of ecosystems. Additionally, proximal remote sensing delivers high spatial temporal resolution with minimal atmospheric interference, which is a key advantage over satellite-based method. This allows for near real-time monitoring of ecosystem dynamics and detailed species-specific observations. So these capabilities complement flux measurement techniques such as eddy covariance for carbon and water fluxes and set flux for water flux. Together, they can provide a more comprehensive framework for integrating and enhancing ecological data. Owing to these capabilities, proximal remote sensing has numerous potential applications, but today I'll focus on my research linking flux measurement with proximal remote sensing in three key areas: monitoring plant responses, tracking phenology, and addressing spatial heterogeneity. First, I'll explain how a thermal infrared camera can capture variation in individual canopy temperatures and how this variation relates to tree hydraulic traits. This study specifically aimed to investigate species-specific canopy temperature regulation using the thermal imaging technique and set flux measurement. We focused on 3 species with contrasting hydraulic traits: Virginia pine, white oak, and southern red oak. The study was conducted in a secondary mixed deciduous forest in Virginia. We used 2 primary continuous measurement tools, one a thermal infrared camera and set flux sensors. The thermal camera was mounted at the top of the flux tower. And here's an example of a thermal image captured by the camera. I identified the canopies of different species and then recorded their temperatures every half hour. Additionally, I measured set flow of the target trees to determine their hydraulic traits and assess their cooling effects. Here's my hypothesis for the study. I define delta T as the difference between canopy temperature, Tc, and air temperature, Ta. I hypothesize that delta T variability is driven by the cooling effect of transpiration, and therefore, delta T variability is linked to species-specific hydraulic traits. According to the isohydricity framework, anisohydric species tend to maintain stomata conductance under dry conditions, while isohydric species reduce their stomata conductance. Since transpiration depends on both stomata conductance and vapor pressure deficit, VPD, it is expected to increase with rising VPD in anisohydric species. In contrast, isohydric species are expected to show little change in transpiration rates under similar conditions. Consequently, anisohydric species are likely to exhibit a greater delta T variability, indicating a stronger capacity to mitigate heat stress compared to isohydric species. Here's a diurnal set flux pattern for different species under wet conditions. Under dry conditions, Virginia pine shows a significant decrease in transpiration, whereas the oak species maintain or even increase their transpiration rates. Based on these responses, the oak species are classified as anisohydric, while Virginia pine is classified as isohydric species. When analyzing delta T, we found that its diurnal pattern varied among the species in both the magnitude and timing of changes. Additionally, the delta T differences between species reached up to 1.5 degrees Celsius. Lastly, we compare set flux and delta T. With changing BPD, set flux variation was more pronounced in the oak species, and the cooling effect reflected as a decrease in delta T was also more evident in this species. And as shown here, our findings support the initial hypothesis. In conclusion, canopy temperature regulation varies by species and is closely linked to species-specific hydraulic traits. Specifically, anisohydric species demonstrate a greater ability to mitigate canopy heat stress. We also found significant differences in canopy temperature among the species, up to 1.5 degrees Celsius. This difference is comparable to the expected changes in surface temperature driven by land use change, highlighting the substantial role of species composition in regulating a larger scale, such as local to regional surface temperatures. And moving on to the tower-based SIF measurement, I will briefly revisit the basics of SIF. So when plants absorb light, the light energy is allocated to different pathways to optimize photosynthesis and minimize photoinhibition. These pathways are photochemistry, chlorophyll fluorescence, and active and passive heat dissipation. This distribution of light energy is represented by quantum fields, where the sum of all 4 quantum fields equals 1. And SIF is a function of absorbed photosynthetically active radiation, APAR, and the quantum field for chlorophyll fluorescence. Similarly, GPP is a function of APAR and light use efficiency. So by combining this relationship, GPP can be expressed as a function of SIF. Then, what does a real-world relationship between GPP and SIF look like on a large scale? This graph shows a time series of satellite SIF in black and GPP in red across 4 different biomes. As you can see, SIF and GPP show similar temporal patterns at coarse temporal resolutions. And on the right-hand side, you'll find a strong linear relationship between SIF and GPP across different biomes. Then what about the SIF at the leaf level? SIF tends to increase almost linearly with rising PAR. In contrast, the carbon assimilation rate saturates at a higher PAR level. Therefore, caution is needed when using SIF as a proxy of GPP, as their relationship may vary depending on the observational scale. So, building on this background, we investigated the influence of vapor pressure deficit, VPD, and absorbed PAR, APAR on tau-based SIF as a proxy for GPP. Tau-based SIF is particularly well suited for this purpose, as it provides high temporal resolution data, making it ideal for capturing the influence of VPD, which can vary significantly throughout the day. Also, the definition of APAR matters, as the interpretation of SIF variation can differ depending on how APAR is defined. This study was conducted in a deciduous mixed forest in Virginia, where I measure canopy temperature using a thermal camera. The SIP sensors are mounted at the top of the flux towers, adjacent to the thermal camera, ensuring both instruments target the similar canopy region. And both SIP and GPP were estimated at half-hour intervals. We tested a different definition of APAR. So the first definition is APAR-M, which assumes that PAR is absorbed by the entire canopy without distinguishing between photosynthetic and non-photosynthetic components. As shown in the graph, the relationship between incident PAR and absorbed PAR under this definition is nearly identical. The second definition is an APAR chlorophyll, which assumes that PAR is absorbed only by functional leaves. Under this definition, APAR is significantly lower than incident PAR. Lastly, APAR was estimated using the scope model, which simulates radiative transfer in leaves, canopy, and soil. This definition assumes that PAR is absorbed exclusively by chlorophyll. And similar to APAR chlorophyll, APAR scope is also substantially lower than incident PAR. So conceptually, both APAR chlorophyll and APAR scope are expected to more accurately represent the actual APAR. There's a time series of monthly GPP for reference. GPP peaks in May and gradually declines over the rest of the season. Tau-based SIF follows a similar pattern to GPP. However, the seasonal pattern of the simulated SIF was slightly different, likely because we did not prescribe potential variability in VC max over time to this model. Let's examine how GPP responds to APAR and VPD. So in the graphs, APAR is plotted on the x-axis and GPP on the y-axis with data points color-coded by VPD levels. And here are the regression lines. We found similar responses across all APAR definitions, and GPP increased with rising APAR and decreases as VPD increases. We conducted a statistical analysis to determine the range of APAR where VPD significantly influenced GPP. The result confirmed that VPD had a significant impact across a broad range of light conditions, regardless of the APAR definition we used. We conducted the same analysis for SIF. The first thing we noticed was the stronger correlation between SIF and APAR, highlighting the challenge of disentangling the effect of VPD from APAR. However, using a more refined APAR definition, we were able to detect a significant impact of VPD on SIF. We directly compared SIF and GPP and identified nonlinear relationship between them. And we also find that VPD significantly affected the relationship between SIF and GPP. Therefore, we emphasize that accounting for the effect of VPD is crucial for accurately estimating GPP using SIF. In conclusion, tower-based SIF measurement provides sub-hourly monitoring of plant responses to rapidly changing environmental conditions, such as VPD. And they effectively capture seasonal variation in GPP, making SIF a valuable tool for assessing plant health and productivity. And lastly, accurately defining APAR and accounting for the effects of VPD and other environmental variables potentially are essential for using SIF as a reliable proxy for GPP. And finally, I'd like to share AmeriFlux resources that support research linking flux measurement with remote sensing. The AmeriFlux measurement project team is currently promoting the Year of Remote Sensing as the slogan for this year's research theme. The goal is to encourage research that integrates eddy covariance and remote sensing across all scales. And our theme year activities include organizing events, providing support for working groups, improving the AmeriFlux website, and offering instrument support. I would like to briefly introduce the last 2 points here. First, the AmeriFlux website now features a web page called Remote Sensing Product. You can find this page under Resources tab. And this page includes an interactive table that provides general information about some of the popular remote sensing platforms, primarily spaceborne and airborne, along with links to their data products. It will help researchers identify which remote sensing products are most suitable for their studies. This page offers various drop-down filters, allowing you to refine your search based on your specific needs. And next, we are collaborating with NASA's GeoNext team, which produces remote sensing products using next-generation geostationary satellite sensors. The new GeoNext page on AmeriFlux website will provide their sub-hourly data sets across the AmeriFlux site, including vegetation indices, surface temperature, albedo, and cloudiness. Here's a preview of the GeoNext page currently in development. You will see grid cells representing flux footprint on the left. There you can select a grid cell to view interactive time series of the GeoNext product. And you'll also be able to download the data directly from the AmeriFlux server. GeoNext data offers a temporal resolution of up to 10 minutes with spatial resolution ranging from 500 meters to 2 kilometers, depending on the product. We believe this high-frequency product will be valuable for both flux and proximal remote sensing communities. And lastly, we'll offer a limited number of proximal remote sensing sensors for free to the AmeriFlux community. So with funding from the DOE, we will purchase sensors to be installed on or near flux towers at eligible AmeriFlux sites. So we plan to survey all PIs in the network select sites, make purchases, and distribute those sensors accordingly. The available sensors include canopy temperature sensors, thermal infrared camera modules, and pyrometers and quantum sensors. So regarding the pyrometer and quantum sensors, we recently published a paper demonstrating how to estimate proximal vegetation indices using this commonly available instrument. This method provides a sub-hourly approximation of NDVI and NIRV, which should intrigue both the flux and proximal remote sensing communities. So with that, thank you for your attention, and I'm happy to take any questions if time allows. Thank you.
Thanks so much. So our next talk is from Adrian Rocha, and Adrian will be telling us about tundra spectral reflectance from fire and nutrient fertilization experiment.
I'm going to share my screen. Well, thanks, everyone, and thanks for giving me the opportunity to talk about my science. It's been great seeing some methodological advancements with near-surface remote sensing, but I kind of want to switch gears and talk more about the ecology and how we can use these near-surface measurements to understand a little bit more about the ecology. And to do that, I'm going to talk about my long-term fertilization experiment that I've been running since 2018. So we have about 17 years of data. In this experiment, we have two sites, one site that was burned in 2007 and another site that was unburned, has no burn history. And we have fertilized about 20 plots with nitrogen only, which is indicated here in N, phosphorus only, indicated by P, and then nitrogen and phosphorus combined. And then the C represents the control. So this is a 2-factorial experiment. And what we're trying to understand here is the goal of the experiment was to really understand the role of nutrients in regulating the successional trajectories or the recovery of tundra systems to fire. In addition to this, we've been collecting in each of these plots leaf area index using the Licor's LI 2200C, which is shown up here. We've been measuring hyperspectral reflectance with an ASD field spec 4, so we get all the way into the shortwave infrared region of the electromagnetic spectrum. And we've also been documenting changes to the community composition using this method that we call the point frame. So this is like a quadrant, and we drop, it's a gridded quadrant where we drop pins, and then we can note what species gets intercepted by the pin, and then we can sort of see the spatial distribution of changes in species composition along with nutrient fertilization and fire treatment. And then the image to the far right here really shows how these systems have changed. So this is our unburned site treatment, and then this is our burned site treatment, which looks a lot different. And at our unburned site, we have shorter canopies, slower growing vegetation. And then at our burn site, we have faster growing vegetation with taller canopies. And so I'll show you this. We published a paper in Global Change Biology a couple of years ago, sort of documenting the first 4 years of the impact of this fertilization. And what we really found in this paper was that if you add nitrogen and phosphorus to tundra, that really simulates what would occur after you burn tundra for a decade, and then allow that burned tundra to recover for a decade. So after burning and after fertilization with nitrogen and phosphorus, you start to see shrubs come in, you start to see a lot of forbs come in, and those are sort of termed as the winners of fertilization and burning. And then the losers of fertilization and burning are evergreen shrubs. So you sort of change the plant functional type from the slow growing herbaceous vegetation, which are short statured, to really fast growing deciduous vegetation that is much faster growing. And this changes the reflectance properties of the surface. And so we looked at 3 different vegetation indices. The Enhanced Vegetation Index, which uses the blue band, the red band, and the near infrared band. And we compare this to the 2-band EVI, which is a band that uses puts additional weight on the red reflectance to account for changes in background reflectance. And then we also compared EVI to NDVI, which is the standard typical vegetation index typically used for tundra. The red points are the burn site plots, and then the green points are the unburned site plots. And you can see here that for EVI, EVI2, and EVI pretty line up nicely 1-to-1. There's very little scatter. But when you look at EVI versus NDVI, you see a lot more scatter. You don't see them going on the 1-to-1 line. That's okay, because they're not designated to go on the 1-to-1 line. But the main point that I want to show here is that there's tons of scatter here, and that scatter is attributed to whether that plot was fertilized with nitrogen, phosphorus, or nitrogen and phosphorus. And you could see that here. The green here is the unburned site plots or treatments, and then the red here is the burn site plots that have been recovering for 10 years. And so each site has quite a bit of scatter around that. Because we measured leaf area index using an optical sensor, we compared the correlation in each treatment. So there's the control plots, nitrogen and phosphorus plots, and the phosphorus plots. The correlation of LAI versus the wavelength measured by the ASD. So what you can see here is quite striking. There are different relationships between spectral reflectance and leaf area, and these depend on wavelength. And what's most interesting thing here, the thing that's most striking, is that the sign and strength of these relationships are not what you would expect. So for example, at the burn site, most of the relationships you see are negative. So you would anticipate using theory that near infrared would correlate highly and positively with leaf area. But here what we're finding is that in these burn site plots, we're finding negative correlations, not positive correlations. And these correlations tend to change at the 2 sites. And they also seem to be consistent with the type of fertilizer you add. So if you add nitrogen and phosphorus, it seems like the canopies get taller and they also get darker, and that influences the correlation between LAI and the reflectance at each one of those wavelengths. So here is the nitrogen and phosphorus one, and that's the one that you see the most negative relationships. So in conclusion here, we found a lot of differences in the relationship between LAI and spectral reflectance that had to do with not only burn history, but also the fertilization treatment that we put on the tundra. We think this has to do with changes in canopy structure and leaf level reflectance. As you fertilize these plots, you see that the leaves themselves actually get darker. And it's actually quite striking how the leaf level reflectance changes across these plots. So this is another sort of example of the power of hyperspectral data and hyperspectral reflectance over just using these simple vegetation indices like LAI, NDVI, and EVI. And that's it. Thank you so much.
Thank you, Adrian. Our final speaker is Baresch, telling us today about trait-mediated continent level responses of vegetation to future climate change, a use case scenario. And a reminder that we'll have an opportunity for discussion after the talk, after this final talk.
Okay, good afternoon. My name is Baresch. I work with Benjamin Potter and David Shimeo at the University of Maryland and NASA Goddard. I'm going to be talking about one project that we put together as starting to adapt vegetation models to incorporate trait retrievals from a spaceborne mission. So this is probably like not particularly new. So leaf vegetation traits and functional rows can be quantified remotely. Then there are missions of NASA that are going to be allowing like a high output, high retrieval rates of these traits and happening wall to wall. Then there are a few missions that are starting to put out data that still falls into an exploratory realm. And yeah, I'm going to be talking about how we can, or how an example of modifying a relatively popular vegetation model called LPJ, a big leaf model, to process remotely sensed traits. And adding some context to why are we using LPJ. LPJ is highly modular. It's a relatively fast vegetation model that acts as a big leaf. So you can actually do a lot of computation. And the idea is that you want this type of advantages for actually absorbing or making using all this trait variability that is expected to start coming in the near future. So I'm going to be talking about one particular mission called Prisma. Prisma is put together by the Italian Space Agency together with NASA. And they have an exploratory, they have sent these scenes. The scenes are at a 30 by 30 kilometer, and we are processing them at 100 and 120 meters. So we have these pixels. They are spread quasi-randomly worldwide, but we're going to be focusing on the tropics.
Excuse me.
Yes.
You're in presenter mode, not in the slide mode. So we're not seeing the slides very well.
Oh.
I think if you click on swap displays at the top, that might resolve it.
So
you're seeing your slides, they were just small.
Is this better?
Yes.
Oh, sorry about that. Thank you for letting me know.
Thank you.
Thank you. So we're working with these scenes. They are spread around the tropics. What we care about is trying to figure out how much diversity is there, but then also seeing if there are consequences from a modeling perspective. The trait retrievals, and I'm personally not an expert in the retrieval side of things. This is put together by Adam Klus at JPL, but relies on algorithms, especially PLSR algorithms in the context of the SVG sister project. And what we are using is also a classification system of trying to focus only on forested areas of the tropics. In terms of these retrievals, I'm going to go straight to showing these. They are, so we see here in green what the outputs from Prisma for these are like millions of pixels for the Prisma compared to two different sources of traits. So you see here, we see chlorophyll, nitrogen, and the leaf mass area, the dry mass of a leaf. These And then compared to Greg Asner 2015, he did plots in the tropics, 0.1 hectare. So what we see is like, at least, even if we are looking at the experimental retrieval techniques, the traits themselves are more or less centered and more or less making sense compared to these sources. You don't expect them to look identical. Everything changes, but at least you're seeing some sense. If you look at them as related to each other, so we are looking at nitrogen concentration as a function of leaf mass area, compared to a global database. This is put together by Sandra Diaz. This is a tribe-based database. You see that they are clustered relatively to kind of like this global perspective. But when you compare it to, again, looking at these calibration sites by Asner, they fall more or less in similar places. What you see when you look at species level, these are canopy cranes that have been worked historically, like there is a lot of data for them. You see that there is a bit more of spread when you're looking at species. So this is always interesting to think about when we are looking at these traits. What you see at forests, at species, is much broader than what you're retrieving at this broad scale. And I'm gonna go quickly here. There are slight differences between continents. So here we have Africa on the left, America, South America in the center, and Asia to the right. There are slight variation in how these traits, when you're looking at all these scenes together. For a modeling perspective, I'm gonna focus on two ways of doing this. One of them is looking at the traits that you see at each scene. This is what I would call like locally observed trait variation for each scene. And then we're gonna look at more like a pan-tropical based on all this observation. So this will be kind of like an ideal other product, getting a sense of exactly how much variation exists in the tropics for traits based on these hyperspectral retrievals. And also from a modeling perspective, we are taking advantage of LPJ having, like, you can run without competition. So you can run each PFT independent, or you can actually allow them to compete. The competition is relatively simple compared to other models, but this serves as kind of like a way of understanding what is going on when you are adding these complexities. This is, I'm gonna go relatively quickly here. This is how we are getting trait retrievals. We're looking at the leaf mass area and nitrogen. We're informing BC max with nitrogen and leaf mass area. And leaf mass area, we're also using it for informing leaf longevity, which turns to leaf turnover, and also how much the cost of a leaf is in the whole budget of allocation. So, and we are going to look at relatively, like, from a very theoretical perspective, we are going to use a very aggressive model of climate change put together in the CMIP distribution. It's called HADGEM. It's a particularly strong warming. So we are forcing this warming and evaluating what happens in this future, in this ideal future. And we're looking at the rate of variation in temperature over the 2040 to 2099 time span. And then we are looking at the annual standing biomass and seeing how it declines. I also looked at the diversity to the right here, but I'm not going to talk about that. I guess time doesn't allow. So we modified an evergreen plant functional type. In order to make sense of the data, you have to kind of like constrain, and not every single scene that was captured actually is capturing this type of broadleaf tropical rainforests that are evergreen. So I do a initial run of LPJ and select only sites where that particular PFT actually thrives. So here you can see the distribution of this to the left, latitude, like in geography, and to the right you can see the kind of like climatic conditions where they are. I want to point out here, for instance, like the African scenes, those are in orange, are particularly dry respect to both Asian and American sites. And let's look at the results quickly. So we have, where is the experiment site? Yeah, so we're doing these 3 different experiments. One of them is looking at these, a lot of traits, a lot of broad trait base. Then we have one that is less like locally informed, so less diversity of traits, more specific to a region. And then we have a way of allowing them to compete. Yes, we have one. Okay. So what we see is, in general, biomass doesn't change that much between the different continents. But when you see the one that allows competition, competition actually has like very, very strong shift towards high biomass. When we look at the change, that rate of change in that period, we also see they are relatively similar, but the one that has competition actually goes to a more dramatic change, a more pronounced change in biomass. And you can look at them in terms of environment, in terms of the climatic variables as a function of them. So you start seeing some coherence. When you're having these models that don't have competition, the changing annual temperature or changing the average annual temperature become like really good predictors or relatively good predictors of what you're seeing in this change. Like, so for instance, warmer sites or sites that are changing faster tend to have like a sharper decline. Also, you see another pattern that is standing biomass here in the bottom. Standing biomass is a good predictor of resilience. So higher biomass places also are a little bit less constrained by this. Now, if you look at the one that has competition, the one that has competition is really messy, and you lose all these correlations. So that is kind of like the message right now. Like if you look at things with competition, they tell you a very different story. You're starting to get like what's called that response diversity, and you start losing kind of like that coherence with climate. So to me, that's kind of like a really interesting message to transmit, and we can leave it there, I believe. Yes, sorry about the time.
Thank you. Thanks to all of our speakers. This was really wonderful. We have a few minutes for discussion. If people have questions or follow-up questions, go ahead and raise your hand or feel free to type it in the chat as well. There's a question for Koong in the chat asking for the tower-based thermal measurement. How was emissivity calculated at the pixel level?
Thanks for the question, Rang. And emissivity, the part of the information is already in the record in the image taken by the thermal camera, so you can learn from it. You can actually learn from the image, but you have to do some calibration over time because it might drift over time. But yeah, the answer is really image. The thermal image itself is containing emissivity value.
How does the thermal image contain emissivity, Koong?
If you look at the metadata in the image, they should have contained some of the information. You can kind of infer the emissivity. Rather,
Yeah, thank you for thanks for the presentation and thanks for answering this question. Yeah, basically I was wondering, like at this fine scale at the pixel level, and you're getting the like different components of that forest, some from the trees, the branches, and some from like the understory, and some probably from those shadows. Then the emissivity must be different among all those targets.
Oh yeah, sorry. Yeah, I think I was looking at reading it wrong. So it's not, you cannot really tell at the pixel level, right? So you have to make assumptions that to interpret the pixels differently. And we have looked up kind of references looking at different levels of emissivity over the different species types and depending on the light conditions.
Okay, thank you.
I have a question for Adrian from the burning experiment. That was really interesting to see the burning fertilization. My question is about NDVI for areas that have been burned recently. There was a preprint recently from the earth science community showing that the year 2023 seems to have had a much weaker land sink than the previous, since 2015 up to 2022. And in that paper, they make the point that in 2023, there seemed to be a decoupling between NDVI and the land sink globally. And they also talked a little bit about, fires. There has been a lot of big fires recently. And so it seems like it raises the question, okay, right after a fire, what happens with NDVI? And you showed some really interesting results, a couple of years after fire, what's happening. So I'm curious if that's kind of a general phenomenon where NDVI is increased after a burn, if you could speak to that a little bit.
Yeah, I published a paper on that fire scar on NDVI in 2010 or 2011. And what I showed in that paper was that NDVI is artificially elevated after fires, especially in severe fires, because what it does is it decreases the background reflectance. And so it changes the impact of the numerator on the denominator for NDVI. So you're artificially increasing NDVI. And that in that paper, we made the argument that using EVI2 was a better measure of greenness and leaf area than NDVI, like immediately after a fire. What we're finding with these results is that, even after 10 years after fire, when the canopy has closed and the canopy has recovered and actually shifted over to a new type of vegetation, we also see a decoupling between the response of NDVI and leaf area that you measure. So we're gonna continue looking at the plot level data, and sort of the next step is to combine that with the point frame data and try to understand how the changes in plant functional type and the community composition impact these correlations between the specific wavelengths and LAI.
Thank you.
I'll add that the other thing that happens after it burns is it burns off all the standing dead material in the canopy, and that affects the NDVI too. So when you get regrowth, even if the green LAI is the same as it was before, the fact that there's no more standing dead also affects NDVI.
Thanks, Fred. It seems like the mechanisms that both of you pointed to would be general, not specific to the Arctic. Would you agree? It seems like any burned area could have those impacts. Yeah.
Oh, you definitely see the difference between burned and unburned on prairies, for example, and like tall grass prairies that we've worked in.
Thanks. For those who are interested, I'll drop the preprint in the chat, and you can check out their final figure where they were showing increase in NDVI in 2023 in spite of the weakened land sink.
I'll add that on the topic of proximal remote sensing, Petya is running a flux at the on the Kanza Prairie right now, and this year the site that was being observed at the Neon Flux Tower site has been burned, and she'll run it next year, so she'll have a comparison between recently burned and then a year after a burned site to see the difference in like the NDVI seasonal patterns from her and well, fluorescence variants from the flux.
Looks like I can have the liberty of another question. Chris, Wong, there was some really nice follow-up questions after your talk about the midnight system and nighttime pulses and looking at fluorescence. And I had asked you a little bit about how much do we know about how the shape might change day to night, for example. I guess if I could ask you to speculate or probe a little more, if you wanted the best representation of your daytime SIF spectrum at nighttime using a system like that, would you perhaps actually want to shine an actinic light first, or like a light that would simulate photosynthesis before before doing your pulse of your light for the fluorescence that was just targeting a specific wavelength?
Yeah, I guess it kind of gets into like where and kind of like the PAM model you kind of want to follow. I guess it wasn't clear in my talk, but basically we turn on the light for the full hour right at midnight. And our light source is fairly weak. I can't recall the intensity off the top of my head, but we were trying to keep it pretty low to not induce any light acclimation to really get at that F0 parameter, that kind of baseline fluorescence. So I think there's like a lot of potential follow-up type questions that could be asked and like developed with these type of methods, like kind of getting towards that pulse type system if you wanted. But we were trying to keep it like fairly exploratory and low cost, and just seeing what we could do with this type of system. But yeah, I think in terms of like the modeling, there could be some like modeling of the spectral response of the chlorophyll fluorescence emissions and linking that with potentially daytime SIF. I'm not too experienced on how that approach might happen. You might be able to use like some type of, I don't know, scope type model or something like that to help feed in some of the nighttime data and then link that with the daytime data. I think the big challenge too might be like the footprint as well, because our system wasn't measuring the exact same thing between midnights and T-Swift. And that's like a big assumption in PAM fluorescence, that you're measuring the exact same thing, both like dark and light acclimated.
That makes sense. It's one thing if you have a leaf in a chamber and you're not taking it out and moving it around, you're just changing light levels. And it's another thing if you're using different instruments and different footprint. Do you have a follow-up question for you in the chat asking, is it possible to use LiDAR for LEDIF measurements? NASA has been experimenting with LiDAR for nighttime greenhouse gas measurements.
Possibly. I guess it depends on the instrument specs, because with ours, we were shining blue light and then recording and measuring the red, far red. So if the LiDAR can kind of follow that, then I think it'd be feasible.
Thanks, Chris. All right, let's let's wrap up. Thank our speakers. Thank you everybody for coming. I really enjoyed this.
Thanks, everybody.
Thanks, Loren. Thanks, Fred. Thanks, Danette. Thanks, Ran.
Yes, thank you all.
Yes, thank you very much.
To all the speakers, good talks today.